All right. All we got left is Q's here, and then we can solve it for the specific heat of the metal. We're getting there. We're getting close. Um, how do we get the Q's? How do we get the heat energy for all of these? We pull in out of our toolbox another equation. Q equals mass times specific heat times change of temperature. That's what those means. That's what those mean. We can always double check if we can't remember, but by the time we're doing our test, we should know what each one of those are. Q is mass times specific heat times change of temperature. Let's write that out for the calorimeter. Mass, in this case, mass for the calorimeter is going to be 5.0 grams. The specific heat is 1.4 so times 1.40 joules over grams times degrees Celsius. And last but not least, the change in temperature is 12.0 degrees Celsius. Almost running out of room. Okay, so what can we do? In algebra, we can do, we can start taking out some of these units, because anything over itself is a 1. Anything multiplied by 1, it's as if it didn't exist, right? Anything times 1 is the same. Nothing changes when we multiply something by 1. So grams over grams, this is on the top. This is the same as saying grams over 1. This is the same as saying 1 over grams. They cancel each other out. Gram over gram equals 1. Take it out. Take it out. Take out the clutter. Celsius over 1 over Celsius over Celsius is also 1. Take that out of the equation. All we're left with on units now is joules. That's a J for joules. And coincidentally, that's what we need our answer to be. Q uses a unit of joules. So we're in good shape here. So now we'll pull out our little calculator. We've got to do 5 times 1.40 times 12.0, and that will get us, and then our answer is going to have joules in it because we've kept that, and that should give us our Q for the calorimeter. Okay, so 5, just write it all out. 5 times 5.0. Only need to be that specific for the answer, but we'll just plug it in just to keep it clear. Times 1.40 times 12.0 equals 84 degrees Celsius. Excuse me, 84 degrees Celsius. We canceled out Celsius. 84 joules. So 84 joules is the answer. 84 joules. Well, let's see. 84. Should we... this is a multiplication. So we got to use, in multiplication, our answer has to have the same amount of the same amount of significant digits as the least amount of significant digits in our measurements. This one has 1, 2. The zeros to the right of the decimal, so that makes it significant. 1, 2. This one, 1, 2, 3. This one, 1, 2, 3. This is the least amount of significant digits. That's what our answer needs to be. So we're not going to say, we're going to avoid saying 0.0. We're just going to say 84. Because that's as precise as we're allowed to be using multiplication. Same amount of significant figures. Okay. 84 joules, that's our Q. So 84 joules, let's put that here. 84 joules. That's how we're going to write it. Okay. So now this might start feeling monotonous, because what do we got to do? We got to do the same thing for the liquid, same thing for our start plugging away our digits for our object, our metal. But notice that we can just do it this way too. We know that mass times specific heat times change of temperature equals Q. So we can just do the equation here. Mass times specific heat, as long as you can stay organized. If this ends up being too much of a jumble for you, write it out again using that formula. But change of temperature, I'm going to try it this way, just to avoid some of the busy work. Once again, we can cancel out our grams. Once again, we can cancel out our degrees Celsius. We're left with joules as a unit. The only unit left is joules, so we'll write that down. And now all we have to do is multiply our numbers. Easy. We can do that. clear it out. Let's start with 150.0. Hey, that's not clear. 150.0. We'll multiply that by 4.184 specific heat of water. Multiply that by 12.0 equals 7,531.2. 7,500. Okay, so that's a big number. How much of this number are we going to use? Remember, this is a multiplication. We've got 1, 2, 3, 4 significant figures. 1, 2, 3, 4 significant figures. 3 significant figures. This is the least precise measurement. So we're going to use 3 significant figures in our answer. 7531.2. We're going to use 7, the 5, the 3, and leave the rest as zeros. Okay? We don't have to round that 3 up to anything because 1.2, that's lower than 5. So we're just going to put 753. 7,530. That's going to be our answer. 0 is not a significant figure, so we're using 3 significant figures here. So we've got two Q's here. We can't do this one because we don't have this piece of information, which is our ultimate objective, but we can use these two to get this, the Q of our object. Let's look at let's pull out another equation out of our toolbox. That is the negative Q of the object. The negative of this number has to be the Q of the liquid, boom, plus the Q of the calorimeter. There it is. So these two added together have to be the negative of this. That can be confusing. That's just, in my opinion, that's opening up a possibility for error. So I have taken the liberty to make an adjustment to this equation. Just did some simple algebra. The equation is the same, only now I have Q of the object equals the negative of Q of the liquid plus the Q of the calorimeter. That, for me, works because once I'm done working this out completely, then I have what I need, the Q of the object. I didn't say what the negative Q is. I wanted to know what the Q of the object is. Q, remember, is heat energy, and as this is all played out, we have gained some heat energy, and we're going to lose heat energy. That's what's happening. So it should end up being the same. The loss should be the same as the gain. Okay, so what we have is Q of the liquid, Q of the calorimeter. Let's write that out. I'm going to put minus, and the Q of the liquid, 7530 joules. 7530 joules. Always put the units. Plus 84 joules. 84 joules. Do our parentheses. We'll contain that in the parentheses and then put the negative. So 7530 plus 84 equals. Okay, we've got an answer, 7614. Should we write it down? Let's think about this. This is an addition. So now we use the precision of the most precise number. The precision of the least precise number. This one, we're good all the way to the ones, 84. The ones are significant. This one, we're precise only to the tens. Only to the tens. So our answer, this is the least precise measurement. So our answer has to be only this precise. So that answer has to be 7, 6, 1, and instead of 4, we're going to round that to 0, 0. And the answer, the units are still there. Of course, we're still contained within our parentheses, and we still have to turn that into a negative. So that means our answer is negative 7610 joules. And let's put that here. Negative 7610 joules. I would be surprised if this was a positive, because typically it's a hot piece of metal, at least it has been for our equations, and it releases heat energy. So that number should be the sum of these two numbers. And the precision, we've got to follow our precision rules to get to the amount of